Hi everyone, thank you for joining today's session. So today is the fourth day of our class. So we had started with the introduction, then we have completed the basics or the characteristics of the RF signal. Then we have in yesterday's session we took up the concept of learning the wireless measurements, and today we will deal with the concepts of antennas. We will look into the antenna concepts. Okay. So as you know, like the classes are from Monday to Thursday. So this is the last session for this week, and we would be continuing on Monday. So Monday, you can see the topic, like what is the topic that is going to start on Monday. So that will be the topic. You can refer to monday.com and you can come to know like what is the topic that is going to start on that particular day. And all the questionnaire that you post on the chat, so that will be captured on the monday.com, and I will be reviewing it and will answer it on the weekends. Okay. Yeah. And also yesterday I have created a document for measurements, since there was little bit confusion on the measurement side, like how the calculation, how the conversion happens between the milliwatt to decibels to milliwatt. So or milliwatts to decibels. So how do we convert that? So there was a little bit confusion. So I have created a document for that. So I hope that makes the concept clear. So before starting the antennas part, so I will just go through that document so you get come more comfortable with that calculations. And one more thing is measurements. The main logic that you need to remember is, if somebody says to you it is a 50 dB signal, so you should be knowing like what exactly the milliwatts for that is, right? So that you need to understand. And obviously nobody is going to ask you like what is a 50 dB, but by at this time, by attending yesterday's session, so you have learned that dB is nothing but a relative value, right? Relative measurement. It is not the exact value or the unit of power, but it is a relative value of power. And since we don't want to showcase the bigger values or the smaller values, because as the signal propagates, the strength of the signal decreases exponentially. So that exponential value is not human readable, or it is very difficult to understand or use in the calculations. So that's why I take a relative value that is 50 dB. Okay. Or that is decibels, right? Deci means 1 by 10, right? So I will walk you through that document. So before going to that, so a few of the points, let's go through it. So wireless engineer should be able to look at the signal and understand if it's a bad signal or a good signal. Okay. Our wireless devices are transmitting at certain power levels. Power levels decrease exponentially as they radiate from the transmitter. We know this. Understanding decibels is crucial for measuring wireless transmission, and received signal strength can be extremely small. When we send a signal through an antenna, so it will be, suppose say 50 dB. Okay, the time it reaches, the user, so that will be around minus 67 dB or minus 72 dB. So this is the value on which, so it is in minus, right? It is very, very low. So minus 67 dB, this is a good signal. Okay. Anything beyond minus 90 dB is not a good signal. Okay. 70, it is like minus 75, minus 80 is also not a good signal. But if you want to have a better data rate, so then you need to have the receiver signal strength should be minus 72 dB. If you are using for voice application, so then the strength of the signal should be around minus 67 dB. So this is the preferred value for voice and data. You can see the values are exponentially decreasing. The strength is basically decreasing exponentially. And why it is, we know that. Okay. And one more thing that you need to remember is I am able to send the radiation and it is able to receive it at minus 67 dB. Okay. But when it is transmitting to the antenna or the AP, so this should be able, this client also should be capable enough to send the signal back to the AP because it is a two-way conversation. So you increase the power of the AP. When you increase the power of the AP, it can travel longer distance. Your radiation, your wave, your signal can travel long distance if you increase the power, right? So if somebody says, I want to send the signal to longer distances, so what is the thing that we are going to change or increase? That is the power, right? When you increase the power, what happens? The amplitude increases. Okay. And suppose you are sending a signal at 50 dB here, but he can send the signal back only at 25 dB, and the distance it can travel is less, maybe the half, right? So then it cannot communicate. It is able to communicate to the client, but client is not able to communicate to the AP. So as a wireless engineer, you should be aware of the specification of the devices. It can be a client device, AP, or it can be a AP or any client device, Android device, Windows. So anything, it can be anything. So it is a two-way communication where both side traffic matters. Okay, where it should, point A should be reachable to point B and point B should be reachable to point A. So that is one thing. Okay. So there is a concept that is dB. dB, we know that decibel, right? Decibels relative to an isotropic radiator. So what is an isotropic radiator? Isotropic radiator is you have an antenna and you are sending the signal radially across that antenna in a 360-degree fashion. So this radial transmission that you are doing, so it is isotropic and it is ideal. So no antenna is ideally isotropic like this. Okay. When we look into the specification of antennas, few antennas you will come to know by looking at some charts. Okay, that is next, that is going to come. But ideal antenna is isotropic antenna which can generate or transmit the signal in a circular manner like this. And when you say dB, dB in terms of isotropic radiator. Okay, isotropic radiator. An isotropic radiator can radiate an equal signal in all directions. The gain or increase of power from an antenna when compared to what an isotropic radiator would generate is known as decibels isotropic. Okay, so when a isotropic antenna generating the signal isotropically, that means in all direction 360-degree. So that kind of antennas power measurements are indicated by dBi. Okay, so when you are sending the signal in all the direction, when you are sending the radiation or a wave, or you are sending the radiation or a wave isotropically, so then it is measured in terms of dBi. Since antennas are measured in gain, not power, you can conclude that dBi is a relative measurement, not an absolute power measurement. Okay, so antenna, when it is providing the gain, that is, it will boost the signal. So the EIRP value is nothing but it is the transmitter power plus loss of cable or any other devices in between plus the antenna gain. So that is the EIRP. right? This is the equivalent isotropic radiated power. So when the antenna gains, suppose transmitter and the loss of cable, so it totals up to 15 dB. The antenna specification says that this particular isotropic antenna provides a 2 dBi of gain. So 2 dBi of gain means in an isotropic fashion, it will give 2 dBi gain. Okay, that's what this I means. A 2.4 gigahertz half wave dipole antenna has a dBi value of 2.14. Now let's see decibels relative to 1 milliwatt. Decibels measures differences or ratios between the two signals. Decibels with respect to milliwatt, that is 1 milliwatt, also provides a comparison, but instead of comparing a signal to another signal, it is used to compare a signal to a 1 milliwatt of power. When you compare a signal with 1 milliwatt of power, for example, if you take 0 dB, what is equal to 1 milliwatt, right? So in terms of when you are referring it dB, you are referring in terms of milliwatt. So then you say dBm. Decibels is a relative measurement. We know that, and it is used in our Wi-Fi communication to to you know, as a unit of not a unit, but for representing the power we are using decibel. Okay, and it is not the exact unit of measurement. The exact unit of measurement is milliwatt. When we reference dB to a milliwatt, then it becomes dBm. Using dBm also makes it easy to calculate the effects of antenna gain on a signal. If a transmitter generates a plus 20 dBm signal and the antenna adds 5 dBi to 5 dBi of gain, then the power that is radiating from the EIRP is equal to the sum of two numbers, that is plus 25 dB. So this is dBm, decibels relative to milliwatt. So that is 1 milliwatt. When you refer 0 dB to 1 milliwatt, the resulting power is nothing but dBm. Okay. So that's why we call it as dBm. Next is antennas. But before going to the antenna, let me bring that picture document to you. Just allow me a minute. Let me switch the screens. Why not it's in positives, as there's a question from Shahrukh, like why not it's in positive as I'm sending 50 dB. If user sits next to AP, so still he gets minus. See, that is isotropically decreasing because the signal that goes out of the antenna, it is going in a 360-degree direction, right? 360 degree. Suppose the AP is here. When you are sending the signal, it is going in all direction, like this, like this, like this, like this. In 3D, if you see, just remember the picture that I shown in the first class, where a person is sticking his hand into a pond and the ripples are generated and it is going radially. Okay, but in just like a balloon, when you blow the balloon, so it goes radially, right? So it goes everywhere. As it goes at the end, it will have less strength. Okay, similar to that, the signal travels in all the 360-degree direction, all 360 degree. To have a better picture, so like this, like this, like this, like this, like this, like this. So here is your here is the AP. Here the signal goes up like this, like this, like this, like this, down. So in every direction the signal is traveling, right? The every direction the signal is traveling. So that is why the power will be less. Okay, the power will be less. The power will be decreasing exponentially. Suppose, just imagine this one. I'm just suppose the AP is here and then a client is sitting here. So it is like 1 feet away from the actual AP. So maybe he is receiving at 3 dB. Suppose he goes another feet away, so then it will be like uh, it will go into minus. Okay. So for every half a distance increase, it will be a half reduction in power. Okay. Every if the distance is doubled, right? If the distance is doubled, then it is a 6 dB loss. That is 6 dB rule, you can say. So every double the distance, when you double the distance, there is a 6 dB loss. If you cut the distance by half, then it will be 6 dB gain. Okay. So that is called as 6 dB rule actually. Yes, minus 40 is a good signal. Okay, minus 50 is a good signal. So that depends on the receiver sensitivity. So in your laptops, there will be the chip that is network adapter or the wireless adapter, right? So that will have a receiver sensitivity of minus 67 to minus 72. So they will be able to understand the signal. That means what? A signal stands with a very good amplitude, then it goes on degrading, degrading, degrading until it fades away. So this, if the signal is received and the amplitude is this much and the signal strength is between minus 67 dB to minus 72 dB, so then it is considered to be a good signal. Okay. Minus 40 is even good because this is minus, right? The lower the value, it is better. Does that answer a question? If he gets minus 40, so will this be better than minus? Yes, of course, it is in minus, right? So lower the value, better the signal strength. So minus 40 means it is a better. Minus 65 is bad, little bit. It is good signal, minus 65 compared to minus 40. It is not that good. After minus 90 dB, so it is a noise. Okay, it is a noise in the atmosphere. So obviously, when you generate the signal in the from the AP, so it's going to travel long distance. So the only the clients will be able to understand between this range, minus 67 dB to minus 72 dB. Okay, let's get on to the other topic. Okay. So this is the document that I shared yesterday. So let's walk through the document and try to understand the wireless measurements. So what is the power? Power is energy applied over a period of time, right? So just remember the example that I gave when you push a door, the push that you are giving. So for what time you have to push? Like maybe for 1 second you need to push, and this much energy is applied to it. So that is what the power is. Power is measured in watts. In Wi-Fi communication, we use power in milliwatts. Wireless transmission power is measured in watts, but typically in fraction of watts. Okay, because if you take watts and in wireless communication, as you know, we send the signal from the AP. The strength is from 1 milliwatt to 100 milliwatt, which is very, very small. So 1 milliwatt is 1 by 1000 watts. That means milliwatts is a fraction of the total watts. 1 watt is 1000 milliwatts. 1000, like if you take 1 and make 1000 fractions of it, so then that is what a milliwatt is, right? So if you take in the other way, that is 1 milliwatt. If you take how many watts it is, that is 1 by 1000 watts, that is 0.001 watt. So this is the watt. 1 milliwatt is equal to 1 by 1000 you need to do. So that much watt it is. Similarly, if you take different values like zero point 0.5 watt, so what is the milliwatt for this? So here you are dividing it if you are converting from milliwatt to watt. Uh, uh, yeah, milliwatt to watt, when you do, you divide it. But when you do from watt to milliwatt, you multiply it with 1000. Why? The reason is simple, because 1 watt is 1000 times milliwatts, right? If you take 1 watt and you cut it into 1000 pieces, that is 1000 milliwatts. So now, if you want to do it in an opposite way, like 1000 watts, when you 1000 milliwatts when you combine, it becomes 1 watt, right? So that's why you need to divide when you are doing it from a watt to milliwatt, sorry, milliwatt to watt, and when you make from watt to milliwatt, then you need to multiply it, right, by 1000 times. So zero point 0.1 watt is equal to zero point 0.1 into 1000, that is 100 milliwatts. Zero point 0.5 into 1000, that is 50 milliwatts. So this is the conversion from watt, milliwatt to watt, and watt to milliwatt. I hope that is clear. It is pretty simple and straightforward, right? And this is the equation that we are going to use, like just power in milliwatts. What is the power in milliwatts? That is 1 milliwatt. Power in watts, you can say, and in 2000, when you do 1 watt is equal to 1000 milliwatts. So this is how you arrive with this equation. So conclusion, to convert watts to milliwatts, we multiply by 1000. Why multiply by 1000? Because 1 watt contains 1000 milliwatts. Every time we move from watt to a milliwatt, we scale up 1000 times. Since milli means what? 1 by 1000. Okay. I hope this concept is clear. And this is some calculations for your reference. Like when we say 0.0001 watt, it is equal to 1 milliwatt. Okay, this dB will come later. So 0.002 watts. So when you do from watts to milliwatts, what are you going to do? You are going to multiply, because watt, when you do from watt to milliwatts, you need to multiply, right? So when you do from milliwatts to watts, you divide. So when you multiply this value with 1000, we get 1 milliwatt. Similarly, when you go on multiplying, so you can see 0.005 watt. So if I want to represent this 0.005 watt as the power of a client, it is little bit difficult. If I say 50 milliwatt, that is more readable, right? So that's why we are converting. That is the only reason for conversion. Okay. Power divided by 1000, power milliwatts 1 by 1000. You can see here. So when you say, see, 0.0001 milliwatt, okay, if you want to convert that to watts, so if you divide by 1000, you can see you're adding some extra zeros here. So that much watts. So when you do from milliwatts to watts, you divide. When you do from watts to milliwatts, you multiply. Then in the next section, you can see here, this is the conclusion. So the same thing that which I explained. So now from milliwatt to decibel calculation. Decibel combines deci means 1/10 and bell. It is on Alexander Graham Bell's name, right? Commonly used for measuring sound and wireless signal. Understanding decibels involve basic knowledge of logarithms. Logarithms, what is the use of log? It helps convert exponential changes into linear scale that we have seen in the studies session. So 0 dB is equal to 1 milliwatt. So this is a reference value. Okay. So 0 dB is the reference point for power measurement in wireless communications. Negative dBm values indicate power levels below 1 milliwatt. Positive dBm values indicate power levels above 1 milliwatt. So above 1 milliwatt, it is positive values in positive dBm. Below 1 milliwatt, it is negative dBm. So with this analogy, you can understand. Somebody asked just now, like whether minus 45 is a good signal or minus 60 dB is a good signal. So anything below 1 milliwatt is goes into minus. Anything above 1 milliwatt, it goes above plus. So with this, what we can understand is, if somebody is telling a value in minus dB, so that means what? It is below 1 milliwatt. If anybody is telling a value in positive values of dB, like 10 dB, 50 dB, it comes between the milliwatts. Okay, that is one conclusion you can draw from this. Okay, and since the values are going in negative in the dBm, so lower the value, so good the number. So that you can remember. Like minus 40 dB, it is a good signal. Minus 60 dB, it is little bit not good but usable. Till minus 67 dB, it is used for voice traffic. Minus 72 dB, it is used for data traffic. So then after minus 90, it is not usable. Okay. So no receiver will be able to understand that signal. The signal is almost like dying and fading away. So let's move on. Converting milliwatts to dBm. Formula used for conversion is 10 into log 10 power in milliwatts. Okay. So just understand this power in dBm. Okay, power in milliwatts. So these two values, power in dBm, power in milliwatts. For example, like we'll come to the example, but just understand this. Power dBm is equal to 10 into log 10 power milliwatts. So this is the formula using which we convert the values from dB to milliwatt. Okay, and why we are adding this 10 and what is this log doing. So if you remember the yesterday's session, why we are using the log function here, because instead of using the exact value, I will use the relative value there. For example, if I take log 10 of 1, log 10 to the power of 1, that means what? 10 I am multiplying 1, so I will write it as 1. Log 10 of 2, that is 10 into 2, 100. So instead of writing 100, if I use a log function, I can write it as log 10 to the power of 2, that is equal to 2. So now instead of representing 100, I am representing 1. Sorry, I am representing 2. 10 to the power of 1 is 1. 10 to the power of 2 is 100. So I represent it as 2. So why this extra 10 I'm adding? So that I will explain here now. So one bell is equal to 10 decibels. Okay. If you take one bell as a unit, so that is equal to 10 decibels. That means what? If you take 1 decibel, you cut it into 10 pieces. So that is 10 decibels, right? So the decibel is 1/10 of a bell, meaning one bell is equal to 10 decibels. This is why we multiply by 10 when converting logarithmic power ratios to decibels. Okay, when we convert dB values to milliwatts, why we are adding this 10? Because we are converting logarithmic power ratios to decibels, and decibel is 1/10 of a bell. So that's why one bell is equal to 10 dB. So that is why this 10 is coming here. Okay. So in yesterday's class, you had the confusion why this we are multiplying with 10. So this is the reason we are multiplying with 10. All right. Why do we multiply by 10 when converting milliwatts to decibels? Instead of dealing with huge numbers like 10,000 milliwatts, we use logarithmic scale to make them smaller and easier to understand. So when we take a logarithmic of a power ratio, the result is too small to be usable. For example, log 10 of 100 is equal to 2. So value of 2 is not convenient for engineers. So we multiply by 10. So to make it as 20 dB instead. Okay. So that is the reason we are multiplying this 10 with whatever the reference value we are getting, relative value we are getting. So with the log functions, we get a relative value and we multiply with 10 because one bell is equal to 10 dB. Yeah. So it is for 100 milliwatts to dBm. Let's convert it. Power in milliwatts is 100 milliwatts, correct? So I take that formula log 10 of 100. So how many times I need to multiply 10 to get to 100? That is 2 times 10 into 10. So that means what? Log this is 2. So this portion will become 2. Why? Because 10, if I want to achieve 100, how many times I need to multiply 10? I need to multiply 2 times. So that's why log 10 of 100 is equal to 2. So instead of writing 100, I am writing a reference value 2. Then I am multiplying that with 10. So 10 into 2 is equal to 20. Okay. So 100 milliwatts is equal to 20 dBm. So here is the chart. You can check out 10 milliwatts you can see, we'll start from here. 1 milliwatt, you can see 10 to the power of 1 is 10 to the power of 1, then 10 into 0, so that is 0 dB. So log 10 of 1 is 0, so 10 into 0 is 0. 10 milliwatts, 10 into log 10 of 10, that is how much time I need to multiply 10 to get to 10, one time. So that is 10 into 1, that is 10 dB. 100 milliwatts, if I want to convert to dB, so 100, I will put it here. So if 10, 2 times I need to do. So 10 into 2. Suppose if you take 250, 10, 250. How many times I need to multiply 10 to get to 250? Okay, that is 10 into some approximate value it will come. It is not the exact value. So you can do the calculator also and you can check out log 10 of 250 and that value will come around 24 dBm. So 500 milliwatts if you take log 10 of 500. So how many times I need to multiply 10 to get to 500. So that value you take multiply by 10, that is equal to 27 dBm. So exact value will not come like with this calculation unless you are using a calculator. But the analogies that you are getting, the observations you are getting, so that is what is important. Okay, you can Google it and you can convert it in like 2 minutes. But on the paper, if somebody asks you to do a conversion, so you should be able to do it with this equation that we are having. So there are three equations that we learned today. That is milliwatts to watts, watts to milliwatts. So that is the takeaway of this document. So when I want to convert from milliwatt to a watt, so what am I doing? I am dividing it by 100. When I dividing it by 100 means milliwatt value, I will divide it by 100. Same thing, if I want to do from watt to a milliwatt, I will take that watt value and I will multiply it by 1000. Then I get a milliwatt value. Okay. So that is the second thing. Third thing is if I want to do a milliwatt to a decibel, then I will use this logarithmic function. And we know how this logarithmic function works. Yesterday also I gave you one example with a graph. So that you can do log 10 of 100. So you can put whatever value you are going to convert there from milliwatt to dBm. And then you get a log value, multiply it by 10, you get a dB value. That's it. See, as simple as that. These are the three equations that you need to remember. Okay. And also one more is there. That is from, we did what? From milliwatt to dB. The next thing is dB to milliwatt. When you do dB to milliwatt, before going to dB to milliwatt, so we'll complete this here. See, this is the positive values that you are converting, right? If you go to the negative values here, you can see log 10.001. So when you do this in calculator, you will get 30 dB. You will get 3. So the easy way to make this out is you count it from this dot, that is 1, 2, 3. So before 1, how many values are there, right? 0 values plus dot. So that you can take, that is 3, 3 into 10, 30. So here you can see dot plus 0, that is 2. So that is like this. So you can do it for these kind of values. You can just analyze it like that and you can tell from milliwatt to dB. Okay, dBm. Suppose if I say 0.001 milliwatt. So what is the dB of it? So 1, 2, 3. That is here 1, 2, 3. So 3 into 10, that is 30. That is 30 minus 30 dBm. See how simple it is, right? So these are the tricks that you need to remember. That's it. Okay. If it is a positive value, 10 milliwatts. So you need to put that in a log function, log 10 of 10. So if I want to achieve 10 and my power is 10. So how many times I need to multiply? One time. So that becomes 1 into 10, that is 10 dBm. So like that you can convert easily. If it comes like 250 and 500, go to the closest value, multiples of 10. So how many times you multiply so that the closest value you reach to the 250. Okay, that you can calculate and multiply it with 10. And why we are multiplying with 10? This is the reason that is over here. 1 bell is equal to 10 decibels. The decibel is nothing but 1/10 of a bell. Okay, that is why we are putting the 10 here. The last one, why we are and the last one is we are converting from dBm to milliwatts. So we are converting, just to summarize again, so that you don't lose the sequence. First we did milliwatt to a watt, then we did watt to a milliwatt, then we did a milliwatt to a dB. Now we are doing dB to a milliwatt. So I am telling dB so that you get familiar, but normally it is dBm. If you remember the previous slide, what was a dBm? When we relate decibel to a 1 milliwatt, that is nothing but 0 dB is equal to 1 milliwatt is a reference value. That is in the metric conversion. 0 dB, 1 milliwatt. From there only we start the conversion. So if we are doing that, then it is dBm. So normally in wireless it is dBm. Sometimes we tell it as dB, but you need, as a wireless engineer, you should know this concept that it is dBm. Why? Because I'm referencing 0 dB to 1 milliwatt, right? When you reference something when you're referencing some dB to a milliwatt, 1 milliwatt, then it is a dBm, right? So sometimes we say it is dB. So that is also fine. So minus 30 dB. So if you want to calculate from dB to milliwatt, you can use this formula. That is 10 to the power of dBm that you want to convert divided by 10. Okay, suppose minus 30 dB you want to convert to milliwatt, just put that minus 30 divided by 10, 0, 0 cancel, 3, 10 to the power of minus 3. Minus 3 means dot 1, this is 1, right? 0, 2, 3, then 1. So like this you can do. Because it is 3, minus 3, right? So dot 0, 0, 1. 3 will be there. 1 is dot, 0 is 2, another 0 is 3. So minus 3 means you can represent it like this. So minus 30 dB to minus, 0.001 milliwatt. Minus 20 dBm to, you can minus 20 divided by 10, it will come as 0.01 milliwatt. So this is not that hard to remember, right? 10 into log 10. 10 to the power of minus 30 divided by 10. 30 is nothing but the power dBm value. You need to put a dBm value, you'll get a milliwatt value in that. So like this you can convert. And you can see minus 10 dB, right? It is 0.1 milliwatt. So 10 to the power of minus 1, that is 0.1. Minus 2 is dot 0, 1. Minus 3 is dot 0, 0, 1. So if you understand that way also, it is very easy to understand. Yeah, so this rule you know, right? Every 10 dB increase, in 10 dB when you 10 times when you increase the dB, so 10x increase in milliwatts. So this I have explained yesterday. So every 3 dB when you do, 2x increase will be there. So here you can see 0 dB, 10 dB. So it will increase 10 times, like 1 milliwatts, 10 milliwatts. 20 you increase, it will go to 100. 10 times power milliwatts is increasing. When you increase 10 times you do a dB, so it will multiply by 10. Okay. So 3 dB, that is double, 2x. 0 dB, 1 milliwatt. 3 dB, so 2 milliwatts. It is 2 times, right? 1, then 2. 2 into 2 is 4, then 4, 2 times, that is 8. So 2 times it is increasing. This is increasing 10 times. 1 into 10, 10, 10 again 10 times, that is 100, 100 10 times is 1000. So every 10 dB signal increase, suppose a client is sitting at 10 dB, okay, and if he travels a few distance, so he will, somebody will say he was at 10 dB, so then he gone to 5 dB, okay, that is like that is in the reverse direction, where he lost like half of his power he has lost. Okay, so in those kind of calculations you can use this analogy. So 10 dB increase, 3 dB and 10 dB increase, that is 10x and 2x. So key points: every 10x increase in power plus 10 dBm, every 10x decrease in power minus 10 dBm. 0 dBm is the reference point of for 1 milliwatt. For every 10 dB addition in milliwatt is increased by 10x. For every 3 dB addition, milliwatts is increased by 2x. If distance is doubled, power decreases by 4x, that is minus 6 dB. If distance is halved, if he was at a 2 feet, he is now at 1 feet. So his dB will be increased by 6 dB. That is a 6 dB rule. So that's what this document is. I hope it was not too much of baggage for you. If you have understood, you can just reply on the chat that you have understood, or if you have any questions, you can ask me for, I can surely clear your doubt on this. I will take that as a yes, you have understood it, or it is too much of a theory for you, maybe. So, so let's move on. So if you want me to stop somewhere and do something different, like go to the next topic and all, so please let me know that as well, because it is kind of a monologue for me where I am only talking. So yeah. Next, this is the fourth topic that we are covering. Why we always say minus 65 is 72 is good. Why we don't say minus 40 to minus 60 is good. Minus 40 to minus 60 is more good. If you are able to get this signal, it is very good. But in real time scenarios, when a user is sitting at a distance from AP, so normally he gets the signal at minus 67 or minus 72, in that range he get. It's not a hard rule. It is a good signal we are telling. That means what? The receiver is able to understand the signal. So what are we doing? So we are sending the radiation out of the AP, correct? So radiation, how it is generated, propagated, first class you need to look at that. So now when you are sending the signal like this, okay, it goes degrading, and and which which the receiver will be able to understand that ones and zeros, right? So if the signal strength is minus 67 dBm, so then the voice traffic the receiver is able to understand and he can interpret that. So that is what that value is. If it is less than that, obviously he can understand better, right? There is no issue. The processing will maybe good. The throughput will be good. So if it is less dB, the throughput is good. The communication is good. Okay, because there are less transmissions that happen. If the receiver is not able to understand the signal, obviously the retransmissions will happen. Then there is a throughput is less. Okay, and the signal that it is receiving, right? The signal that the receiver is receiving, he is able to understand whether it is a 1 or a 0. Till what extent he can understand is minus 67 dB. So that's a good value where the receiver can understand. If it goes beyond minus 67 dBm, that is minus 68, minus 69. So this is a not good value, right? Compared to this value, because the higher the value, because it is in the negative minus, right? It is not a good value. So till minus 72 also good. Sometimes minus 75 is also good. But if you go beyond minus 90, it is a noise. You will not, the receiver will not be able to understand whether it is a 1 or a 0. If it is like minus 80, it might struggle to understand whether this wave, whether the radiation, the sine wave that you generated, right? So whether it is a 1 or a 0, it will not be able to understand. So then it has to do a retransmission, and here it is not a retransmission. Uh, yeah, here also you do the retransmission. It is somewhat different than the normal Ethernet retransmission. Okay, that we'll learn later. But for now, you understand that minus 65 is a good signal and 40 is also a good signal. Okay. Okay. I hope you got this concept. Okay. Let's not spend too much of time on that. Okay. So what is an antenna? So we are learning about the antenna, which is the most critical component of the wireless. Okay. Because with the antenna only, we are going to say spread out our communication in the network. Just like the Ethernet cable, The antenna is the critical component. If the antenna is not there, obviously you're not able to communicate. There are many types of antennas designed for many different purposes, just as there are many types of lights designed for many different purposes. When purchasing light for your home, it is easy to compare two lamps by turning it on and checking if it suits your room or a lobby or outdoors. But choosing an antenna is not that simple. You have a bulb in your home, and that bulb is suitable or not. You can light up the bulb and you will come to know. But if you walk into a shop of a antenna provider or the antenna shop, so you cannot just on it and see if that is how it is covering weather, because you cannot see it. That is the reason. If you want to purchase a bulb, you go, you light it up in the shop and you can see that bulb. But if you go to a shop where you are purchasing antenna, so you cannot do that. You can walk with the RF meter and you can check how far this antenna can send the signal, but that does not tell you like whether it will cover radially, circular it will cover, in a horizontal fashion it will cover, in a vertical fashion it will cover. So that is not possible. So the way the radiation goes out, right? So that is unique. That depends upon the antenna type. Okay, there are many types of antenna, so that we will see one by one here. Okay, so while purchasing the antenna, so there is one important thing that is called as charts. So every provider like Cisco or any other antenna providers, vendors, so they provide the charts, azimuth charts. By looking at those charts, you can come to know, you know, you will come to know about the radiation that they are going to emit, in what direction it will be, what is the orientation that you need to keep. Suppose you have an antenna that is outdoor antenna, so their orientation is very important. And also in office, corporate offices, you hang the antenna on the ceiling. So if that antenna, yeah, if that AP has an antenna and that antenna is oriented towards above, so then that does not make a sense. That has to be inverted and it has to cater the users in downward direction. And I don't want the radiation to go on the top, right? Because nobody is there. So it has to cater at the bottom. So choosing a right antenna is important. But normally in the indoor scenarios in a corporate office, the antennas are like inbuilt. They are patch antennas. They are inbuilt into the AP. So there is no much there's no much things that you can do. Suppose in rare cases, because it in real time scenario anything can happen, right? Maybe your requirement is not downwards but little bit slanting towards this, and most of your employees are sitting at this place. So then how are you going to you know, how are you going to place that antenna? Obviously, it is attached to the AP, but is there any setting that you can do? You can influence that radiation towards those users who are sitting in the room. So those all things we will see. So it is a big piece of metal. It is a passive device. It means no power. So antenna is a passive device. What is a passive and active device? So obviously the transmitter is going to generate the AC signal, and we know how the AC signal is generated. Once the AC signal travels on the copper wire through the antenna cables and the lightning arresters and some multiplexers or signal boosters, it will go, and then it will reach the antenna, right? So now the antenna is depending on the power that this transmitter has generated, maybe 10 dB of power it has generated by reaching to the antenna. It is like 8 dB. This is the IR value. So then it will add 2 dB. This antenna specification, while purchasing the antenna provider told you this antenna will provide a 2 dBi of gain. When the antenna provider told you that it is going to provide a 2 dBi of gain, I means isotropically, that means it is an isotropic antenna and it provides the radiation in 360-degree direction. Okay, 360-degree direction like this. There will be antenna that are focused antennas that can take this radiation that is going radially and can focus only in a particular direction. Okay, particular direction. So that is the second step. So first step, what you want to understand is, so now this 2 dBi gain, whatever it is getting, so how it is getting? So I am not putting a power source here and boosting the signal here. It is just a piece of metal. Then how it has got the power, how it has got, what is making to increase the power? So that is when we discuss any antenna, so we take the ideal scenario. Every antenna is an isotropic antenna which radiates radially everywhere. But these antennas, what they do, instead of the in real time world, instead of going in all the direction, so they focus in a particular direction. So that provides the gain. So you are not doing anything extra here. So it is like a water gushing out of a pipe, and uh, that pipe, what you can do is you can streamline that water. So whatever the water coming out of the pipe, you can streamline the water. So when you streamline that particular water, you can increase the speed of the water. You will increase the speed of the water, but the water that is present, so same water you are taking and increasing the speed of the water by channelizing it properly. So that is what here also happening. The signal that is there, so you take that signal only, and instead of radiating in all the direction, you're focusing at some point. So that makes it to have a more gain. So the energy that was radiating in all directions, the energy that was radiating in all directions, so that will not happen and it will focus. And since it is focusing that energy, so that's why it will have a gain. Okay, it will have a gain. For example, you take a balloon, you have a balloon. When you squeeze the balloon, so what happens? It will create like a donut shape. Okay, so now the balloon was like this, like an isotropic thing. Now when you squeeze the balloon, it takes a shape of a oval shape it will take. So now the energy is focused here. So now the distance it will, the distance is more here like this. Okay, so that is a passive gain. Passive gain is because you're not charging anything and boosting the signal. So whatever the signal is present, that only you are channelizing it, you are focusing it at a particular point. So that makes a gain out of the existing signal. Okay, that is the antenna gain. In transmit perspective, we use AC voltage concept to send out wireless signals, and at the receiver end, we catch the wireless signal and convert to AC voltage and read by receiver. No power boost. We are just shaping the signal. This is the word. Okay, we are just shaping the signal. When we catch the wireless signal, we are converting it into AC voltage that is read by the transceivers. We compress the signal instead of letting it go in isotropic fashion. The total of outputting power remains the same. Only thing is we make the signal strong near to the radiator where we measure gain of the antenna. So this is the picture where you can get the idea what I am talking about. So if you take the isotropic antenna, that gain is 0 dBi. That means there is no gain. But when you try to focus it, as you can see, this is the outer one here. Low gain, wide beam width, shorter distance. This is medium gain beam width. The beam width will decrease. As it decrease, the gain will be more. Okay. As you start focusing more, the gain will be more. Very narrow bandwidth, long distance. Okay. So we have learned the characteristics of the RF waves. Okay. So that has a amplitude, frequency, phase, all these things. And also one thing that you need to understand about this radiation, RF radiation is, it is just like a balloon. Okay. when you compress, you generated some radiation, right? So by using the antennas, what you can do is you can kind of you are taking your two hands and pushing it and pushing the balloon, right? So it creates this oval shape. So that is how this radiation behaves. Okay, this is the way it behaves. So that's the analogy about the passive gain. I think the time is up, 9:30. I didn't notice the time. So I hope you understood this analogy of antenna. I was hoping to complete this by today, but since the calculation was pending from yesterday's session, so I was not able to move to this antennas and complete it. But yeah, in the next session, we would be looking more deeper into this antenna stuff, and we would be understanding the azimuth chart, elevation, and all these things. Okay. Sorry, I took your extra 2 minutes, but yeah, so we will continue tomorrow. And next session is on Monday. And I request you to join exactly at 8:30 IST. Okay. So yeah, that will help to complete the syllabus on time.